In question 1, we want to test whether the frequencies of phone calls are all the same for each day of the week. Now, I've copied these observed frequencies here already into Excel. I've copied the observed frequencies here. The next thing I want to do is I want to state the hypotheses for this test. Now, the probability that a phone call comes in on a Sunday is 1 in 7 if the phone call frequency is the same for every day of the week. And if that's the case, the probability of a phone call coming in on a Saturday, Monday, Tuesday, Wednesday, Thursday, Friday, or Saturday, they're all the same. In other words, the null hypothesis can be restated as, is this distribution uniform? Are the phone calls uniformly distributed across days of the week? Thus, the null hypothesis in Cengage Now is going to be stated as the distribution of phone calls is uniformly distributed. The alternative hypothesis, there exists one day, K could be Sunday, or it could be Monday, or it could be Tuesday, or it could be Wednesday, or it could be Thursday, or it could be Friday, or it could be Saturday. There's one that stands out. So one of these above does not equal the other. Another way of stating that is the distribution is not uniformly distributed because there's one that is different than the others. So the alternative hypothesis in Cengage Now is not uniformly distributed. Next, we're going to get the number of calls in the sample. To get the number of calls in the sample, we just sum the calls for each day. The total number of calls in the sample is 2,475, and we're going to paste that into Cengage Now here. Next, we have to compute the expected frequencies to 2 decimal places. If the probability of a phone call coming in on a Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, or Sunday, if those probabilities are all the same, then the expected frequency should be all the same. And to calculate the expected frequency for Monday, we take the total number of calls for the week and multiply that by the hypothesized probability. Now, after I hit enter, I'm going to pull this down to get all these other expected frequencies. And when I do that, this box is going to come down one at a time. And we want to freeze this box. So I'm going to click on C22 and hit the F4 button to freeze the blue box in cell 22. So the expected frequencies are all the same. We multiply each probability by the total. Now, if we did this right, the sum of expected frequencies should be equal to the total number of observed frequencies, which is the case. Now, I needed these to 2 decimal places, so I'm going to copy one of these and then paste it here, here, etc. Now we need to compute the sum of expected frequencies, and again, remember that was equal to the sum of observed frequency. Next, we have to compute the test statistic to 4 decimal places. To get the test statistic, what we have to do first is subtract the observed frequency from the expected frequency, and then do that for every day of the week. Next, we're going to square these deviations from expectation. Next, we're going to divide what we just did, the square deviation from expectation. We're going to divide that by the expected frequency for each case. Test statistic is just the sum of that final column, 9.7002. Now, the intuition behind the test statistic is this. If the observed frequencies are about the same as what we expect, in this case we expect uniform, then these values over here are going to be quite small. However, we have this Sunday value. The Sunday value contributes the most to the test statistic. Now, why is that? Well, Sunday call volume is much lower than what we expected if phone calls are independent of days of the week. So this value here, which corresponds to the Sunday observed frequency, contributes the most to the test statistic. Now, is that enough to make this test statistic large? If the test statistic's large, then we conclude what? The distribution is not uniform. How do we know if this test statistic is large? Well, we've got to compare it to critical values. Before we do that, I'm going to copy this value into Cengage now. Okay, the degrees of freedom are equal to the number of categories minus 1. And we have 7 categories, so the degrees of freedom here are 6. We want a 5% level of significance. So we're going to go to the chi-square table. We're going to go to row 6 and column 0.05. Okay, we're in column 0.05 and row 6. So the critical value is 12.592. To conclude the test, we have to compare the test statistic to the critical value. Now, if the difference between the observed frequency and the expected frequencies are 0, then our chi-square test statistic is going to be 0. Because these are all going to be 0, these are going to be 0, these are going to be 0, and there's some of 0. So the closer the test statistic gets to 0, the more evidence we have in support of the null hypothesis. The further this test statistic gets from 0, the less evidence we have in support of the null hypothesis. But this value is not bigger than the critical value. So we're going to conclude by saying that we cannot reject the null hypothesis. In other words, it appears the number of phone calls is roughly the same for all days of the week. And then we're going to check our work. We should get everything correct. And we do. In problem 6, we want to test whether milk consumption in the Midwest is at least 21.6 gallons. At least means greater than or equal to. So the statement shaded in blue is the null hypothesis. Greater than or equal to 21.6. So if the null hypothesis is the mean is greater than or equal to 21.6, the alternative hypothesis is less than 21.6. Now, this is a sigma unknown problem because the sentence that starts with a sample ends with standard deviation of 6.9 gallons. So that is a sample standard deviation. This is the sample mean, 22.8 gallons, and the sample size is 53. So I'm going to copy 53, X bar 22.28, and S, the sample standard deviation, into Excel, which I've already done. So the sample mean is 22.28, the sample standard deviation is 6.9, and the sample size is 53. In part A, we need to determine the critical value. The significance is 10%. The critical value is going to be negative. The critical value will be negative because the alternative hypothesis says mu is less than 21.6. The alternative hypothesis is indicating a lower tailed test. So with a significance level of 10%, a one-tailed test, we divide the alpha by 1 because it's a one-tailed test. The degrees of freedom are 53 minus 1, 52. So we find the t critical value, which is negative, in column 0.1 and row 52. So column 0.1 of the t-table and row 52, thus the lower critical value is a negative 1.298. Now we're testing 22.28 against the hypothesized value. The hypothesized value is 21.6. So the point estimate of the difference between the population mean, 22.28, and the hypothesized value, 21.6, is positive 0.68. The sample variance is the square of the sample standard deviation. The variance of the sample mean is smaller than the estimated variance of the variable because the variance of the sample mean is equal to the estimated variance of the variable divided by the sample size. The standard deviation, or standard error, of the mean is the square root of the variance of the sample mean. The value of the test statistic is the ratio of the point estimate of the difference and the standard error. So I'm going to copy these one by one into Cengage now, starting with the test statistic. The test statistic to 4 decimals is 0.7175. The standard error to 4 decimal places is 0.9478. The point estimate of the difference between the population mean and its hypothesized value to 2 decimal places is 0.68. The point estimate of the population mean, which came from our sample of 53, is 22.28. And the critical value, which is a negative value because it's a lower tail test, the critical value was a negative 1.298. To conclude in part G, we have to compare the value of the test statistic to the critical value. And since the alternative hypothesis is mu is less than 21.6, if we have evidence in support of the alternative, the test statistic is less than the critical value. That is not the case. So we cannot reject the null, which means we cannot say the alternative is true. We cannot conclude that milk consumption in Webster City is less than the national average. We check our work and we should get all green check marks, which we do. In problem 4, we want to know if year-end bonuses are different than 125,500. So this is a two-tailed test. If the mean year-end bonuses of a particular company is different than 125,500, then the alternative hypothesis is true, and it would be the mu is not equal to 125,500. The opposite of that is mu is equal to 125,500. Now, because this is a two-tailed test and sigma unknown, now, why do I know it's sigma unknown? Because this sentence starts with a random sample has an average of 119,250 and a standard deviation of 33,323. Now, because this is a two-tailed test and sigma unknown, the significance level has to be split in two, and the critical value will be found in the column corresponding to alpha divided by 2, 0.025, and the row corresponding to 52, because the degrees of freedom for this problem is the size of the sample, 53 minus 1. With a sample size of 53, the degrees of freedom are equal to 53 minus 1, and the alpha is divided into 2. So we're going to go column 0.025 and row 52 to get the critical value. In column 0.025 and row 52, the critical values are plus or minus 2.007. So in part B, I pasted in the critical values, plus or minus 2.007. In part C, I need to enter the answer for the point estimate of the population mean. The point estimate of the population mean is not equal to 125,500. It is 119,250 because we're testing 119,250 against 125,500. We're going to copy 119,250 into part C without a comma, because sometimes Cengage Now does well with commas and sometimes it doesn't. And we're going to paste it next to X bar. The sample standard deviation is 33,323. The sample variance is just the square of the sample standard deviation. The hypothesized value is 125,500. The point estimate of the difference between the sample average and the hypothesized value is a negative $6,250. The variance of the sample mean is less than the variance from the sample because it's the estimate of the variance of the variable divided by the sample size. The standard deviation of the sample mean, also known as the standard error of the mean, is the square root of the variance of the sample mean. The test statistic is the point estimate of the difference between the population mean and its hypothesized value and the standard error. Next, we're going to copy in the point estimate of the difference. We're going to copy that into Cengage Now. And we need 0 decimal place accuracy. Next, we're going to copy in the standard error of the mean. And we only need 2 decimal accuracy. So if I get rid of the 6.1, I'm going to make that 7. Then we got to copy in the test statistic to 4 decimal places. To conclude in part G, we have to compare the value of the test statistic to the critical values plus or minus 2.007. If the test statistic is in between plus or minus 2.007, then this difference is insignificant. And we have evidence in support of the null hypothesis. So that is the case. The test statistic is in between these two values. So we cannot reject the null. Since we cannot reject the null, we cannot say the alternative hypothesis is true. Thus, you cannot conclude that the year-end bonuses paid by Jones and Ryan were different from that of Wall Street securities firms. We check my work. We get all questions right.